So I have a question. Jeremiah, right? Jeremiah had a great idea that the data presented in this scatter plot, i.e. the data from back in the previous data set, is predictably increasing. There's a pattern in there. So if I asked you what right now, what the number of Americans under 65 with no health care number would be, what would you tell me?
Under 65 years of age?
Under 65, so this data set, Americans under 65 with no health insurance.
Sorry.
That's okay, that's okay, that's okay. I'm trying to keep it to as simple as a data set as I can.
Well, it's probably like 150 million because Obamacare is working.
Can you say that again?
Wow.
Speaker.
Well,
Can you say that again?
see, that's what's interesting. Not to get political, but millions more now have it.
Right.
But
They don't.
I do. I can show you sources.
No, yeah, I know.
But time out now. I don't want to get a fist fight because you'll kick my ass. Based on this data, though, assuming that Jeremiah's pattern, which I love by the way, thank you, Fred, assuming that pattern continues, it's Trey, you're correct in saying it's going to continue to go up, obviously. I mean, based on this pattern, it's going up anyway. My question is, if you had to assign a number to how many would have, or not have health insurance
Are uninsured today?
in this year, 2014. Maybe we'll go 2013 because 2014 just started. So let's say at the end of 2013, what number would you apply? What number would you tell me?
Like 55.
I hear 55, 48. Tell me, can I ask where your numbers are coming from? Chelsea, go ahead.
Well, I was just kind of looking at like the way that the pattern was going.
Okay,
So, like,
and so what did you see? What did you see?
well, I saw like the first one, it went from 35 to 38.
Right.
So that's a nice little increase.
That's 3,
But
yeah?
then when you go up to 2000 or to 1998 to 2000, it's kind of the same.
That's 3 as well, yeah?
Yeah.
Over 2 years.
Yeah.
What are we looking at right here? Oh,
So we're looking at 3 times
slopes,
10 to 30.
grades.
Yeah.
Making me happy.
Average.
Now it's a little skewed in how I presented it. Again, this is 2 and this is 3. Technically speaking, if this was a 1-to-1 scale, this should be 1.5 times as big as this. So don't let that mislead you. Look at the numbers themselves. So can we do all of it, Chelsea? This here?
Yeah.
What would that'd be what, 2 over 2?
2. Yeah.
There's your 100% grade.
And
Now realize that 100% means absolutely nothing in this context because it's uninsured per year. Whereas all those grades you guys were doing were feet per feet, and that's why your grades have no units on them. Everything slope-wise has a unit on this graph because it's millions of uninsured per year. Does that make sense? Good, hopefully, good. And then here, how about this guy?
that would be 2 and 1.
2 over 1.
This 1 and 2, yeah? 1 here and then 2 here. Good! So how can we use that data? Tell me your name again.
Debbie.
Debbie, thank you. Are you using that data to make your prediction?
Well, yeah, well, can you take then the average
Oh, why
of
not?
those?
Why can't you?
And then,
From
well, yeah, the
So
average. you
the
say
average
get
of
an
3, 1, 2, and 3?
Yeah, you would get to take the average of that.
So,
and
so
then-
what Debbie's saying, and this I think is what Trey and Chelsea were getting at too, you're using those slopes to kind of guide where you're headed. I love that idea. So let's average the slope. So first of all, let's make it a little more concrete. We're assuming that there is a slope in there. This goes back to what Jeremiah said about predictably changing, predictably growing as time goes on. So we've agreed there's different ways to be predictable. When we measure me going careening somewhat out of control on my bicycle down the hill and you're timing me, that's predictable too, but in a very, very different way. It will not be predictable in this way. But this appears to be predictable, and it looks to me like you guys are looking for a line that's going through. So as far as mathematical modeling goes, it seems like you guys are leaning towards what's called a linear model. Hopefully this term means something to you from your previous math classes, linear model. When we say something is linear, what do we mean?
Straight line?
Well, absolutely, it's a line because it comes from the idea of a line forming it, good. And what makes it a straight line? What makes it a line?
2 points.
Oh, good, 2 points determined. Who said that? That was wonderful. Jacob, thank you. 2 points. Anybody of you guys ever use a chalk line to set a line for construction? You take one end and tack it if you're working by yourself or have your friend hold it, you drag that chalk line out and you put the other end where you need the straight line to be, and that thing lays down a perfectly straight line. Now you can put lots of different shapes through those 2 points, but only one's a line. So what's the deciding factor between 2 points that makes it a line and not something like a parabola or a sinusoidal? Tom?
Shortest distance between the 2 points.
I like that answer. It is the shortest distance. It's the shortest distance. Good, good. I bet you didn't learn it that. That's perfectly said, by the way.
Exactly how I
But
learned it way back.
oh, back in geometry class you did. But in algebra class, they don't talk about short distances. They talk about the changes in x's and y's are what? Oh, I think I'm asking the wrong question. So, when Debbie?
Yeah.
Is that right? Debbie. When Debbie told me to write these slopes out, or Chelsea, both of you guys I think had me to do it, what did you notice about these slopes? Ish. They're almost what? Well, 3 over 2, 1 over 2, 2 over 2, 3 over 2. You're telling me to take an average of all of them to get one that stands for all of them. That's because they're all pretty what to each other? They're pretty close to each other, yeah? Like there's not one that goes like 8 over 2, or 13 over 2, or -5 over 2. There's no great deviations in behavior. Let's go back to Jeremiah's first definition of predictability. They're pretty close. They're not perfect, are they? They're not perfect, and they shouldn't be perfect. If they're perfect, that's why Harrison Ford had to run away in The Fugitive, and the guy with the one arm was trying to kill him. Because the data was too perfect. Remember the whole point of that? I'm sorry if nobody's ever seen this movie before. I just ruined the kind of surprise for you. But the data was too perfect, and he realized that it was too perfect, and it turns out it was forged. Now that doesn't give away too much, I don't think. But the idea is data is never perfect, but data implies something, and this is implying a straight line. So that's why we're calling it a linear model, because the slopes look pretty consistent, don't they? The slopes look pretty. And now Debbie's saying, wait a minute, I wouldn't call those consistent because they're not close. 1/2 is not 3/2. I'm with you, sister. I'm with you. But when you first looked at that graph, and when you first looked at it, does your eye kind of see a line through it? Kinda-ish, yeah? Kinda-ish. And that's the idea. Now the question is, sorry about that. What line? What line do we see? So I'm gonna pause and restart again and resume. No, actually, that's pretty good.